Hi guys, welcome to the next lecture. Today we will talk about some important aspect of continuity. We will talk about the continuity of polynomial functions, rational functions, and also when you take a composition of two functions which are continuous, will the composition be continuous? So how do you in general show that a function is continuous everywhere? The general way of showing it by showing that it is continuous at any arbitrary point. For example, if we have a polynomial px and we want to show that this polynomial is continuous everywhere, we would like to show whether it is continuous at any arbitrary point, say A. So say A is an arbitrary point. Arbitrary means random. We would like to show that Px is continuous at this point A. Now, for continuity, what do you require? You require that the limit as x tends to A of Px should be equal to Pa. And by the limits of polynomials, we actually know that limit of a polynomial at a particular point is nothing but the value of the function at that point. And this will happen for any A that you will take in the domain of the function. And hence, a polynomial is always continuous. So that's the special thing about polynomial functions. They are continuous at every point in the domain. And here I would also want to talk about the rational functions. We have already defined what a rational function is. A rational function is basically the ratio of two polynomials. And as polynomial functions are continuous, the ratio will also be continuous as long as the denominator is not 0. So all rational functions are also continuous, just like the polynomial functions, as long as the denominator is not equal to 0. Let's state these couple of facts formally now. So point number 1 that we made, all polynomials are continuous everywhere. A polynomial function is continuous everywhere. Number 2, a rational function is continuous at every point where denominator is not equal to 0 and has discontinuity where the denominator actually turns out to be 0. Let's take an example. For what values of x? Is there a discontinuity in the graph of x square minus 9 upon x square minus 5x plus 6? Where do you think you will have discontinuity? As mentioned, where the denominator is actually 0. You will find the point, the graph to be discontinuous there. So let's work it out. Let's find out for what x is x square minus 5x plus 6 equal to 0. Whenever you have to find points of discontinuity, this is what you will do in case of rational functions. So clearly, I think I can factorize it. Minus 2x minus 3x plus 6 equals to 0. That means I will get factors x minus 2 minus 3 x minus 2 equals to 0. So x minus 3 into x minus 2 equals to 0. So whenever x would be equal to 3 or x would be equal to 2, and these points you will get the denominator to be equal to be 0, and hence the function, the graph of the function, in other words, it will be discontinuous. Let me take you through the rough graph of this function. You can also try it out. You must actually pause and try to graph it yourself. What is happening here? At 2, you will see that you are getting asymptotes here. What you can see is that x equal to 2 is like asymptote here, right? But there's quite high chance that you would see that there is sort of continuity at 3. You will easily find discontinuity at 2 because you will see that asymptotic situation, but not at 3 graphically. It is happening because your function is x square minus 9 upon x square minus 5x plus 6, which you can simplify as x minus 3 into x plus 3 upon x minus 3 into x minus 2. So x minus 3 cancel out here, okay? And the function looks, in a simplified manner, looks like x plus 3 upon x minus 2. But as I've taught you before also, the domain does not include 3 and 2. 2 is very much visible after cancellation as well, but the function is not defined at 3. So graphically, you might feel that there's a smoothness here, but the functional value would not be there. So you don't have a functional value at 3. So therefore, it is a discontinuity, a removable type at 3, but not at 2. At 2, you have discontinuity because the limit only, it doesn't exist. It is plus infinity and minus infinity. But at 3, what you can see here is like this. By the way, if you observe at minus 3, when x is equal to minus 3, the graph will cut x-axis here, and that's why the hyperbola sort of shape is going like this here. Okay. So I hope this is clear conceptually what's happening here. The function or the domain of the function would not consist of 2 and 3 if the function is defined like this. Clearly, the denominator is 0 at 3 and at 2. So these are your 2 points of discontinuity. So graphically, if you would have seen it, then maybe what would have happened is that you create a smooth hyperbola on the first quadrant as well. On the first quadrant, as it is a smooth hyperbola on the, down here. But it is not a smooth one here. You do have a break because F3 is something that you do not have. So there are still 2 points of discontinuity until and unless the function has been defined in some other way. When I say in some other way, they have defined that F3 equals to actually the limit that it is turning out to be. So this was a special case that I wanted to discuss. Apart from this, I also want to discuss another special case. Let's see to it. The special case that I actually wanted to discuss is modulus x. Modulus x is continuous everywhere. Why is that happening? Because modulus x is equal to just x when x is greater than or equal to 0. It is 0 when x is equal to 0. So I could actually take strictly greater than 0 in the first point. And then it is negative of x minus x when x is strictly less than 0. So what we're trying to say is that in the interval open 0 to plus infinity, it is x. In the interval minus infinity to 0 open, it is minus x. In the individual domains, if you see in the individual domain, open 0 to infinity, the function is just x. It's just like a polynomial function. It's just like any other polynomial, and we've already seen that polynomials are continuous. So it is continuous everywhere. And if we talk about minus infinity to 0, since the function is minus of x, it is again just a polynomial. So it is continuous everywhere, which tells us that the point of confusion could only be x equals to 0. Because around 0, in terms of the function, I can see you have x and minus x. So do we have a problem here or not? Let's see. So at 0, there might be an issue, but the best way to check is to check the continuity using limits. So for continuity, we require limit as x tends to 0 of the function should be equal to the functional value at 0, right? That's what we want to show. Now, the limit as x tends to 0 could be seen from the left-hand side and from the right-hand side. So the left-hand limit and right-hand limit, when you are looking at the function from the left, that is x is less than 0. So the function is minus x. And when you're looking at the function from the right, that means the domain is 0 to infinity, the function is x. But the value as x is tending towards 0 of minus x will also be 0 and of the function x will also be 0. And that's what is the functional value at 0. And therefore, the function is, therefore, modulus x is continuous at x equal to 0. And for that matter, if you ever see the graph of it, I'm sure this is one graph that should be imbibed in your head by now. It just goes like this. It's a V-shaped graph. There's a sharp bend here and it turns into V. So there's no smoothness here. There is no smoothness here because you have a kink here. But there are no breaks, no gaps. Hence, this function is continuous. The last thing that I want to discuss in this video is the continuity of compositions. So suppose you have a function gx and you have a function f. Function gx is such that the limit as x tends to some point c of gx is defined as L. It's a finite limit. And suppose f is a continuous function at L. F is continuous at L, and what is L? L is the limit of gx as x tends to c. Then that means you can apply f considering the composition f of g. So limit as x tends to c, f gx is nothing but f of L. So what are we trying to say here? We are trying to say that the limit as x tends to c of f gx is equal to f of the limit as x tends to c of gx. So basically what we're trying to say is that you can limit of the composition becomes functional value of gx here. Limit of f gx is nothing but f of limit gx. So we can do that because f is continuous. And this concept will remain the same whether x is going to c plus, that is, right-hand limit, whether it's about left-hand limit, whether it's about x going to plus infinity or it is going to minus infinity, that will always remain same. So in case the limit of gx exists, it's finite, it's L, and there is a composition f of g, and f is continuous. Then f limit as x tends to c, f gx is nothing but f of the limit gx. We have just seen that if I take the function fx as mod x, this is a continuous function, right? Mod x is a continuous function. Let's take a function g which has a limit at certain points c. So let's take gx as some polynomial because I know that the limit would exist. So let's take it as 5 minus x squared maybe. And let's consider the limit as at 3. Just randomly, let's consider limit at 3. A polynomial has a limit everywhere, so it has a limit at 3 also, right? So what I'm trying to say here is that if you are asked to find the limit as x tends to c of f of gx, in our case, it would become limit x tends to 3, f is modulus. So f is nothing but modulus of the input. Input is gx. So input becomes 5 minus x. So we are talking about modulus of 5 minus x square as x tends to 3, right? A modulus of 5 minus x square. What's going to happen here is this will be just equal to modulus of the limit as x tends to 3 of 5 minus x square. Both the things will be the same. It won't be different. I specifically taken 3 because that would give me a negative value inside. So the limit would be absolute value of 5 minus 9, which means minus 4. Absolute value of minus 4 is 4. So the limit would turn out to be 4. And in case you would have, just taken the limit first, limit of gx as x tends to 3, you would have figured out that the limit is minus 4. And then if you want to find out limit of f of gx, you could have just done that, okay, that means absolute, because fx is modulus x, that means modulus of minus 4, and yes, it is 4. So that's what modulus would do to the limit, and that's what composition does to a limit. Now, this gave us the idea of how to find out limit in case of when f is continuous and we have a limit for gx, how to find out this limit, right? What in terms of continuity it is telling us? It is telling us that if a function g is continuous at c and f is continuous at gc, then the composition f of g is continuous at c. And on the other hand, if the function g is continuous everywhere, that was just a point. Now, if g is continuous everywhere and f is continuous everywhere, then the composition is not just continuous at c, but it will be continuous everywhere. And it's pretty easy to see how. So I'll just try to give you a brief, case. So whenever we are looking for continuity, what are we checking? We are checking that the limit should be equal to the functional value, right? So the functional value, if we are looking at limit at c, at a point c, so functional value will be f of g at c, right? So let's consider the limit. Limit x tends to c of f of gx, right? Now, I know what is f of g. F of g is f of the input gx, right? Now, by the theorem that we just did, or by the definition that we just did about limits, so we know that this is equal to f of, I can take the limit inside because the limit of g exists. That's an assumption that we are taking, right? So it becomes this. And since g is continuous this time, now we are talking about continuity. G is continuous at c and f is continuous at gc. So g is continuous at c, that means the limit will be equal to the functional value at c. So what do I get? I get f of gc. That means by definition of composition, this is nothing but f of g of c. F of g at c. So what we wanted, we have proved that the limit is equal to the functional value at c. And if it is happening for all c's everywhere, then it's going to be continuous everywhere. So if the two functions are continuous everywhere, the composition will be continuous everywhere. Composition of two continuous functions is continuous, but not the other way around. This is food for thought that I'm giving you. Put your thinking caps on and try to figure out, in case a composition is continuous, would that imply that both the functions have to be continuous? That's all I wanted to discuss in this video. Thank you.